And today we're going to talk about one of my favorite topics, DFAN testing, which stands for direct field acoustic noise. So we got some slides and then we'll go into the software and see how some of this works. This is a glossary of terms and abbreviations that we use in vibration test. DFAN testing, what's it all about? Well, rocket ships and stuff. We have all this stuff going on when we do a space launch. There's the engine and booster ignition and combustion, which causes all kinds of things. Air and structure-borne sound. There's all this loud noise that comes from all these different sources. And inside the fairing, where you have your test article, satellite or CubeSat or some type of reusable launch vehicle. So we have all these sources of noise that can affect what's inside the launch fairing here. There's also satellite release noise and stage separation and all these other things that we have to deal with when we are launching something into space. So all of these different sources for noise and vibration can affect the payload and also the launch vehicle. We typically have a launch vehicle user manual that tells us all of these different vibration environments that anything strapped to the launch vehicle has to survive. So we have sine vibrations, random vibrations, acoustic noise spectra, and shock spectra that are included in this launch vehicle manual. And when we strap something to a rocket and launch it into space, we have to do all of these tests to make sure that once we get whatever our payload is into space, it still works. There's some challenges with designing payloads. There's this trade-off between weight and then structural risk of something going wrong. We always have to do 100% testing on everything that's launched. And there's a risk of damage during testing. And the big thing here, as I mentioned, is whatever we're launching has to be right the first time. You don't get a second chance. You don't get to bring a satellite back into the shop and fix it once it's in space. And if it gets to space and it's broken, you have several $1,000,000 chunk of space junk that's just floating in orbit. So we do all this testing to avoid that problem. And today we're going to talk about specifically the acoustic portion of the testing, but we go through all of these different tests for spacecraft verification and qualification. There's shock and sine and random vibration tests and modal and some micro vibration or subcomponent vibration tests that happen as well. There are two methods here for the acoustic qualification. The widely accepted and historical method has been this reverberant field acoustic testing. Today we're going to talk about direct field acoustic testing. And you might be asking yourself, well, what's the difference here? The traditional reverberant acoustic test, or RFAN test as it's called, has to have a specialized facility. So you have this acoustic chamber, and it's not quite so clear in this chamber, but there's this big, thick concrete door that slides across this threshold here and closes the test article in completely in this reverberant chamber. These cost millions of dollars to build, and you can't move them, and you pump nitrogen through these horns, and it bounces all over and creates this acoustic field that affects your test article. With direct field testing, or DFAN, we don't have noise that's bouncing all over the place, i.e. reverberating through this chamber. We point the speakers directly at the test article and blast it with sound. And so what you have in this RFan setup is infinite reflections of sound bouncing all over the place. You can see this is a view from the other side with the door closed of that same chamber. And you don't have to think too much about the field in here, because the noise field, the sound field, whatever you want to call it, pressure field inside of here is uniform by the sheer fact of the design of the chamber. The challenge in DFAN testing is we're using the direct field from these speaker stacks, and you have no reflection, so you don't have any help in making this field uniform aside from what your controller can do to change the field inside the test circle. So why would anyone ever do a DFAN test if RFan is so much easier? Well, it's all about risk mitigation. If you are designing a space vehicle and you want to do a reverberant test, what you have to do is go to a reverberant chamber. That means packing up your test article, bringing it someplace by truck or rail or something else, maybe an airplane, and shipping it there and setting this all up. And not everybody has access to these reverberant chambers. There's only a handful in the world. They're very expensive to build and expensive to maintain. DFAN has the advantage of being able to break down this setup and set it up in any test lab anywhere. So you're bringing the test to the test article instead of bringing the test article to the test. And that significantly reduces risk of damage to the test article through shipment or setup or things like that. Because essentially you're building this around your test article. Let's take a look at some of the differences here. RFan, you have very simple control. It's a traditional approach, but it's expensive. There's risks in and expenses in transportation, and the operating cost of RFan is significant. With DFAN, you don't need a dedicated facility, much lower costs, no transportation for the space hardware. You have a lot of flexibility with the schedule because you're bringing this in. So if it slips, you can wait a little while. If you slip here, you might not have access to this chamber for a while until the next opening is to run it. DFAN is more recent than RFan in the last 20 or 30 years, so it's not as mature as these RFan tests. And you have challenges with creating this uniform acoustic field. But with some recent developments, we have gotten much better with doing this. Another comparison that's often made is you have this reference signal in red here, and you can see DFAN has much better homogeneity at the lower frequencies and a little less uniform at these higher frequencies. However, one can argue that the lower frequencies are creating most of the damage. So these higher frequencies, while still important for electronics and stuff, aren't as damaging to the actual structure of the test. So maybe even DFAN is superior because you get better results at low frequencies, but everybody has an opinion about that. I'm just pointing out some of the differences. So again, up top here is the RFan tests, and you can see the microphone responses in this setup versus this setup. It's same test article, same microphone setup, just RFan versus DFAN, and again, lower frequencies versus higher frequencies. You can see the differences there. Now, the other thing to mention is reverberant chambers are typically CISO or SISO control, which means single input, single output. So you have one drive out to the horns and the reverberant chamber, and you have these microphones that get averaged together into some control spectrum, and it's much like a single axis shaker test. Initially, DFAN was approached in the same manner with the SISO controller. And you get high correlation between responses, but not very good control. And high correlation between responses is pretty bad in this type of testing because you want your sources to be uncorrelated to get a uniform sound field and avoid standing waves and other things that arise from having correlated sources out to the speakers. So what ends up happening is you get pretty bad uniformity, and in order to control the field uniformity, it's highly dependent on the microphone setup. Now, MIMO control is a much better option for DFAN testing. MIMO stands for multiple input, multiple output. You have a number of different drives that the controller can adjust that go out to the speaker stack. So you get the correlation that you want between the responses and not uncontrollable correlation. And as a result, you get great uniformity, and you use all these microphones controlled simultaneously. Here is an example of the experimental data. You have this CMO approach in blue, the MIMO in red with a 3x12 rectangular control, MIMO in green 6x12 rectangular control, and then the results from the reverberant chamber in purple. Now, as the reverberant chamber is the traditional method, we're trying to do with DFAN is match what the reverberant chamber is doing as much as possible. And you can see here the significant deviation in a CMO controller versus the MIMO control, which overlays pretty well with the reverberant chamber. Here's a picture of a setup, and you can see all these speaker stacks. Gets about 150, 145 dB inside this circle, which is enough to stop your heart and kill you. So pretty powerful sound field coming out of here, and these speaker stacks are, depending on the venue, sometimes there's more speaker stacks in a DFAN test than you would have at a large stadium rock concert, depending on, again, the venue. So lots of speakers, lots of sound pressure, and lots of vibration happening here. So let's take a look at DFAN in a little more detail. So as I mentioned, that the main goal of this DFAN test is to obtain a sound pressure field that's similar to the sound pressure field inside the launch fairing. So this is an example of a fairing. The test article goes in here, and we take a look at the vibration in here and come up with this reference profile that we want to replicate. And you also have some specific coherence profiles that you want to try and match as well. And where does this reference come from? Well, again, this launch vehicle manual gives you these references, but a lot of times it doesn't give you a coherence reference. So that can be challenging to come up with. So the setup for DFAN, you have high-powered loudspeakers, you have high-frequency speakers and low-frequency subwoofers, so that you cover the entire frequency range that you need for the test. The crossover frequencies typically in the range of 30 to 40 hertz. So the subwoofers handle sound less than 30 hertz, and the higher frequency speakers handle sound higher than that, with certain roll-off between the high and low frequency speakers. You have amplifiers and digital signal processors that are connected to all these speakers, same as an amplifier and a shaker. Then you have microphones that are used both for control and for monitoring. The test article may be instrumented with accelerometers, strain gauges, et cetera, and then you need to have this control and data acquisition system. Here's a SCADAS lab, and you have all these sources going out to the separate speaker stacks so that they can be controlled individually and thereby better control the uniformity of the sound field. And we use this MIMO control to do this, and you do this with narrowband PSDs up to 146, 150 dB. It's a closed loop control. You need to take the sound pressure levels from the launch vehicle manual, convert that to control PSDs, and then you generate this matrix of control PSDs, phase and coherence. And we can also do some pre-test analysis, which is recommended. So we'll take a look at some of that stuff. So here's a typical setup in time lapse of setting up a DFAN test, and you can see they start putting the speaker stacks together and all the amplifiers. See the control microphones getting set up here. That's the SCADAS lab for all the channels, shot of the controller. Here's putting the test article into place. More microphones, finishing the setup of the speakers, and finally actually running the test. So a lot of effort goes into that. And here's some examples of acoustic test specification. You have some qualification levels in dB, sound pressure levels. You have an overall sound pressure level, you have a duration for the test, and then you have tolerances on top of that. Now, when we're doing this, there is an overall control channel that includes all of the control microphones. We call that the spatial average. And then you can look at each individual microphone as well versus the test specification. It's called a uniformity check. Control strategy gets a little complicated here. We have this whole matrix solution that you have to invert in order to get the drives that you need. So this matrix has PSDs along the diagonal and then coherent spectral densities in the off-diagonal terms here. You can imagine that can get a little complicated to control. But major questions: how do you define this target matrix? Where do you place control microphones? And how do we ensure that we're getting the right level and a uniform sound field? Let's talk a little bit about that. In a SISO system, like you might be typically used to, or RFAN, there's one measurement that's taken as control, call that Y. You have some kind of drive, we'll call that U, that's coming out of the controller. And then you have this transfer function, or FRF, that you're able to deduce through some pretest analysis, and that's multiplied by this drive signal to get this output. What we're doing here is inverting this, multiplying by the control spectrum and figuring out, after some corrections, what our drive in voltage needs to be. These are scalar values, so the math is pretty straightforward. You have this drive multiplied by the transfer function, that's going to get you your responses, or what's actually happening is you feed this back and figure out what your next drive has to be, versus this reference spectrum here. Again, you're basically inverting this transfer function, dividing the reference by that inversion to get your next drive. And you update that FRF constantly through the test by just dividing these spectra, output and drive. Now with MIMO, it gets significantly more complicated because you have your response matrix, which is a vector. You have your drive matrix, which is also a vector. And then your transfer function matrix becomes this L by M matrix, which is the number of responses or controls by the number of drives. This causes a problem because you have this rectangular matrix most of the time. And inverting a rectangular matrix is not possible with traditional linear algebra. You need to have a function, and note here, this is kind of telling. The traditional way to denote an inverted matrix is the matrix to the -1, but we have this little dagger symbol that we're using, and that's for a particular purpose. We'll get to that in a second. So again, reviewing these issues, right? If you have a square matrix, there is one solution to that inversion. If you have a rectangular matrix, i.e. the number of drives and control channels are not the same, you have two cases where the number of responses is greater than the number of drives. You end up with this overdetermined system. You don't have an exact solution. And then you have this other case where the number of controls is less than the number of drives. That's an underdetermined system, which has infinite solutions. Well, we're not going to do that. That's a problem. But what we can do is apply a least square solution to this overdetermined system. And this is a process called pseudo-inversion or singular value decomposition. I'm not going to get too far into the math. I know that's very disappointing for all of you out there. But the basic idea here is in square control, you have one solution. You have good matches at your control points, but potentially large error at measurement channels. With rectangular control, you are expected to see some errors, but you avoid large errors because you spread that error over multiple control channels. And that's this least squares method. A little bit about it, this singular value decomposition of this FRF matrix that we have. You have vectors U and V that we talked about earlier, but you have these singular values representing the dynamics of the system. And then you have to take this pseudo inverse in order to come up with a least squared solution. You have an issue with some of the lower singular values. If they're low and very affected by noise, increases uncertainty. So test setup can be very important here. A couple of notes. Pre and post test is important. We can create a digital twin of the test article and the speaker stacks and do some pre-test modeling with that, but also when we do pre-test with the control system, we put out some white noise and basically measure the initial transfer function matrix. But we have some algorithms here that can optimize the selection of control points to get the best fit and the best spatial uniformity. And we'll take a look at that. In the software, you put in your one sound pressure level profile, and then the software calculates the best solution to that. And we have some enhanced reference profile techniques and stuff here to minimize error. And you can see with the standard control versus this enhanced or advanced control strategy, we get better results. The last thing to mention, in a post-test kind of situation, we can take the time data from this test and then be able to do some operational modal to see what the structural dynamics of the test article are and get some mode shapes out of it. So that's kind of a neat feature of the software as well. So let's take a look at the controller. All right, this is the MIMO control module in SimCenter Test Lab. And what I'm going to do here is just load some previous data here so we have something to work with. Obviously, I don't have a full MIMO setup in my office here. First of all, my wife would probably leave me if I was playing noise all hours through a speaker stack. So this is some data from another test. Channel setup, pretty straightforward, nothing special here per se. When you do set these tests up, you do want to do in situ calibrations of the microphone, and we do have a module for doing that. It's an add-in. This calibration here. You can also turn on time-domain storage. And the calibration routine is pretty straightforward. You put in your Pistaphone information here in Pascals, and you can do the calibration of each microphone individually. It's pretty straightforward when you get into it again. Then we go into the MIMO random setup. And of course, we want this acoustic mode with spatial averaging. And we put in all our control specifications here, just like a random test. All this safety and schedule stuff. Again, this is very much like running a single shaker random test, and you start at a lower level and then you ramp up, keeping an eye on field uniformity between the microphones as you go. Then you come in here and you can put in your reference profile. Tests are generally specified in third octave bands, and these are the third octave band center frequencies. In this case, the test rig we were using, we didn't have any particularly low frequency speakers, and they only went up to 5 kilohertz. So this is the test setup for our example set, but pretty straightforward. And then the next step is doing this system identification, which is a pretest, sends out. I guess one more thing to point out here is note that we're using multiple drives here. For the traditional kind of single shaker test, you'd be using one drive. So we have 6 outputs here. And then each one of those outputs puts out some random vibration here. You can shape these spectra, as you can see down here. These were shaped to roll off at higher frequencies, because you generally need most of your excitation down at the lower frequencies to run the test. Then once you have this data, you go into system verification. There's some cool tools in here. You can take a look at all the channel ranges. You can take a look at all your open loop thresholds that are set and be able to modify these if you need to. You can look at all the different drive predictions, and you can look at all the different predicted responses based on the system transfer function. But we also go one step forward and do some actual pretest analysis. And what you do when you set this up is you mark all these microphones as control. And then once you get to system verification and the pretest analysis, what we can do is choose how many microphones we actually want to pick for control. So for example, if I want to use all 12, I can put 12 in here and pick a number of iterations and combinations, and the software goes through and iterates. And in this case, we have one solution. But if we take a look at this, we might see that some of this isn't really so good. So maybe we'll try excluding some microphones and see if we can get better option here. You can see now I have a lot more options to pick from, and this is different combinations of reducing the number of control channels from 12 to 10. And if we take a look at all of these, we can see the kinds of things that happen here. So in this case, it looks like we have 1, 2, 3, 4, 5, 6, 7, and in this one, 10 and 11 were excluded from control. And we can see what all those responses were. You might find, looking at the drive, that you're getting a solution here that maybe isn't the best, right? This output 2 is more than some of the other options here. And you can see we cycle through and take a look at some of these other selections. We're basically sacrificing tolerance and error to take a look at what we might be able to reduce these drive levels to. You can see in general, this output 2 is being driven the hardest. Maybe that was due to the setup. Maybe the gain out to that speaker was less than the other ones, but you can kind of see here, this solution has a lower drive level than some of these other options. And again, we can change the number of channels and iterate again. And we get back to that solution here. Or maybe I want to try 8. So you can take a look at all these different possible setups and try and find the best solution for your test. The other thing to look at here is we have the geometry with all the microphones. You can see which microphones in the geometry have been excluded from control based on our settings here. So anyway, that's the pre-test analysis, long and short of it. You can also look at the drives individually. We can look at the singular values and the inverse transfer functions as well, this inverse transfer function matrix. MIMO, the actual random control portion, not particularly different from single shaker random test. You hit ARM and you hit start and it starts going. So that is the kind of executive overview of DFAN testing. Feel free to reach out to me, chrissensor@siemens.com, or follow me on LinkedIn. You can also take a look at our Siemens community site. This is a link to our index of all the different knowledge base articles that we have. And thanks for joining us.